And you can go ahead and start that up. Well, good evening, everybody. Let me begin by thanking all of you for coming tonight. Once again, it's an expression of citizen concern and citizen seriousness about what Terry correctly pointed out is a problem of global dimensions. I also want to thank explicitly all the organizers. I can't name them all by name, but thank you all for putting this all together so that we can all get together tonight. So I'm glad Terry went first, because it turns out that I have quite a few things here that will hopefully be seen as a direct refuting of some of the things that he said. So the question that we're supposed to be addressing tonight is, should New York State and/or Starkey Township allow high-volume shale gas extraction? I don't think you're going to be surprised. How do I make this thing work? Oh, I don't think you'd be surprised with the answer. That's the most complex slide you won't see tonight. But obviously, I have to give you my reasons. I don't want to be glib. And I'm going to focus on two reasons. And for each of those reasons, I'm going to actually use a quote from my colleague, Professor Engelder. So I'll let you read this one, but I'll read along with you. This quote appeared in an article that was published in the Village Voice a few months ago. Terry and I were both interviewed for it. And it says, where the science of fracking is concerned, engineer Tony Ingraffea and geologist Terry Engelder agree on almost everything except this. Tony thinks fracking should stop. These are Terry's words. Tony thinks fracking should stop, and I don't, says Engelder. I believe that economic health has to come before environmental health is worked out. Tony is arguing for environmental health at any cost. You effectively heard Professor Engelder say the same thing in different words just a few minutes ago. So the two reasons why I think the answer to the debate question should be no, this is one of them. Yeah, that cost is too high. That environmental and human health cost is too high, and I hope to try to convince you at least partially of that over the next few slides. So reason number one, going back to what Professor Engelder said, is I believe before you set policy, before you expend billions of dollars of investment that could be going to green energies, before you establish regulations for fracking, high-volume fracking in New York State, first you do the environmental assessment and you do it correctly. And you establish what the real costs of those environmental factors are. And we have not done that in New York. The debate question is about Starkey, and it's about New York. And in New York, we still don't know the answer to how much will it cost us. So I'll give you a couple of examples of the cost. And of course, those of you who have heard me speak before know that the cost all depends upon the fact that this is shale gas. It's all about the geology. And as you've heard me say many times, it's about the fact that to economically develop shale gas, one has to use unconventional means to develop natural gas from shale formations using multi-well clustered pads with high-volume hydraulic fracturing from long laterals, AKA fracking. So Chesapeake shows you this wonderful artist rendition of this bucolic setting with very, very little footprint left after they drilled, in this case, 4 pads. It looks like 6 wells from each pad, and here are the long laterals. What they don't show you is what that actually looks like. So what it would look like in this area is every one of these yellow rectangles, I think we're somewhere in here in this picture, every one of these yellow rectangles is a spacing unit, 1 square mile, 2 miles long, a half mile wide, oriented north, northwest, south, southeast, thanks to Professor Engelder's research. And every red square would be roughly the location of a pad. And so in the ideal setting, this is what the area around here would be like. A pad roughly a mile, mile and a half in each direction, 2 miles in the direction of the drilling, roughly a mile and a half orthogonal. And so you would see in this area a large number of pads. And Terry pointed out something which is not quite correct. He said he corrected me for saying that there would be 16 pads per mile. But in fact, he didn't go back and actually look at the talk I gave containing that slide, because on that slide it says, this is not what it will look like in shale gas. I'm aware of that. What it will look like is that, and I can prove it to you, because that's what it looks like in Pennsylvania right now. So let's go to Pennsylvania, and let's go to Tioga County, not too far south of here. Here's a map of Tioga County put together by Shell. Shell has leased up about 30% of Tioga County. And this is their map given to the EPA of what they intend to do with their lease holdings. And as you can see, all these little rectangular units, I'm blowing it up here so you can see it, is a spacing unit oriented roughly north-northwest, south-southeast. Each black dot is the location of a pad, and this is called spatially intense development. Clustered pad arrangements, a grid work of pads, multi-wells, 6, 8, 10, 12 wells per pad. So what? That's the economical way of developing shale gas. What does it mean in terms of the all-important risk to human health and the environment? So there are many things we can talk about with respect to risk. Terry brought up the word. He focused on a couple of things and said I wouldn't talk about the water. But I am going to talk about the water. I'm going to talk about the local effect, someone's contamination of someone's underground source of drinking water, their private water well. And I'm also going to address in my second reason, the global effect, climate change, as Terry has. So what happens when you have this many wells on this many pads in an area like this? Well, what you actually see is not that bucolic, beautiful Chesapeake artist rendition, but you see things like this. These are actual photographs of pads in various stages of development in Pennsylvania. They're not 2 or 3 acres. They're large. They involve a lot of not just pads, but ancillary infrastructure, compressor stations, if the gas is wet, processing stations, thousands of miles of pipeline, and in New York State, if we're going to see 100,000 Marcellus and Utica wells combined, we're going to see 7, 8, 10,000 pads and 100,000 wells and hundreds of compressor stations. And obviously, this is an industry that in every state so far, except for New York, doesn't have to abide by everything that every other industry has to abide by, and that's zoning. This is the only industry in every state so far, except New York, that requires us to live in their industrial zone. Every other industry is required to live in their industrial zone while we live in our residential zones, our school zones, and our commercial zones. So it's not that bucolic setting. And remember, Terry pointed out there are 6,500 some Marcellus wells in Pennsylvania. Only about half of those have been fracked so far. And Professor Engelder assures me that he expects about 100,000 wells in Pennsylvania. So what have we seen in Pennsylvania so far? You're just getting started. So any deleterious effects, any problems that you've seen or read about, it's the tip of the iceberg. This is a heavy industrial activity and accidents will happen. Professor Engelder pointed out, and I agree. The question is, what is the risk? Quantify it. Quantify it in terms of number of incidents and quantify it in terms of the number of health repercussions and the number of dollars spent to rectify those problems. We don't know the answer to those questions even after 5 years of development in Pennsylvania. So how can we possibly project them with New York? So I am going to talk about the water. And sir, if you can put the cursor on that image and click on it, some of you know what a leaking well looks like. Some of you don't. That's supposed to be a video. It's going. There we go. This is the production casing, the steel pipe that's supposed to be bringing Marcellus gas up from underground in Pennsylvania. And as you can see from the bubbling in this little cellar full of water, a lot of the gas is coming up outside the production casing. That is a trademark of a well that has lost structural integrity. It's a well that is leaking. It's a well that has failed. It's a well that, because it is leaking, will do certainly one thing until that leak is fixed. And if it can be fixed, it's putting methane into the atmosphere. And Professor Engelder and I agree that that's a bad thing from the climate change point of view. It might also be causing whatever is bubbling up, which could be methane or other hydrocarbons, to come into contact with an underground source of drinking water, hence contaminating a water well. So let's talk about risk. How frequently does that happen? So Professor Engelder showed you an old slide that I show from Canada. You remember that one you saw a few minutes ago? 350,000 Canadian Rocky Mountain oil and gas wells that were surveyed. and he said, see how much the industry has improved? Now only about 2.5% of the wells leak immediately, whereas 20 years ago, 10% of the wells leaked immediately. But what he didn't say is that that data is transient. What that one graph doesn't show is that a well, if 2.5% of the wells leak immediately, a higher percent leak as they age. And what he didn't show is the best data you can possibly see. It's the data that your New York State DEC should have showed you. This is the data that should have been in the SGEIS. It should have been the data that formed the basis for the proposed new regulations. It's data I sent to the DEC a year ago. I sent it to them again 2 weeks ago. Here's the data. What is the best data you can see? Ask yourself that question. We want to assess the risk. How frequently do Marcellus wells fail? Not Canadian Rocky wells, Canadian Rocky Mountain wells, Marcellus wells in Pennsylvania, drilled and operated by the same operators we would expect to operate in New York State. There could be no better database. So I went into the database. A colleague of mine at Cornell, we went through 6,500 well records, 6,500 inspections for all those wells. And we counted the number of times the Pennsylvania Department of Environmental Protection had found wells that were leaking. I'll let that sink in. And what we found is that of the 1,609 wells in Marcellus that were drilled in Pennsylvania in 2010, 6% of them were leaking immediately, brand new. Fast forward to 2011, the failure rate went up to 7.1%. Fast forward to 2012, the failure rate went up to 8.9%. So where's this improvement that we expect as industry gains experience? They're going in the wrong direction. And in fact, that data mimics the data from Canada and the data from offshore wells, which draws me to the following conclusion. The industry is doing as well as it can. That's as good as they can do. If they could have done better, they would have done better. They don't want to lose product. They don't want to cause wells to fail. So that's it. Now, if Pennsylvania's experience in the last 3 years is somewhere around 5, 6, 7% of the wells are going to fail immediately, and remember, every failed well is a potential source of contamination of an underground source of drinking water, and it's certainly emitting methane into the atmosphere. Let's do some basic arithmetic. We expect, according to DEC, between the Marcellus and the Utica, somewhere around 100,000 wells in New York. If 6, 7, 8% of them are going to leak immediately, how many are going to leak immediately? Hundreds? Thousands. What's the economic cost? Do we know? Should DEC tell us this? Should it be part of the economic evaluation before we proceed with changing the policy of New York State or the town of Starkey? I submit the answer should be yes, we should know. So, I'm just repeating, every one of those leaking wells does two bad things. One locally it could contaminate an underground source of drinking water, or more than one. One leaking well doesn't necessarily impact one person's water well. But they will also, as long as they continue to leak, emit methane and other hydrocarbons into the atmosphere and cause exacerbation of global warming. So that caused me to write a couple of recommendations. In fact, I sent 32 pages of recommendations to DEC on January the 10th. I don't expect you to read all these, but one was DEC should develop its own prediction of immediate and long-term rate of well failures for shale gas development in New York. Of course they should. They had the same database that I had. They should be able to do the same analysis that I did and get roughly the same answers. I'd like to have my analysis verified or invalidated by DEC. Unless they do that, I know of no rational way of costing the risk. Risk is all important, as Professor Engelder said, but it's just a word. It doesn't mean anything until you cost the risk. So how do you cost the risk of repair of thousands of water wells? How do you cost the risk of exacerbation of climate change? Is it possible to do that? Yes. Has it been done in New York? No. So it's not possible to perform a rational cost-benefit analysis of shale gas development in New York without a science-based, probabilistic estimate of the number of expected well contamination incidents due to faulty wells and DEC should estimate the impact of such emissions on New York State goals for reduction of carbon dioxide and its equivalents. So I want to point out that Professor Engelder in his opening comments was focusing on the most important greenhouse gas, carbon dioxide, but he didn't say too much about the next most important one, methane. I'll come to that in a few minutes. In fact, I'll come to it right now. I told you there's two reasons why I think the answer to the debate question is no. Here's the second one, and again, I start with a quote from Professor Engelder. This one appeared in the Ithaca Journal. I don't know where the original source was. So he was asked about the role of renewables, and as you just heard him say, he is very much committed to moving the U.S., as I am, and the world towards renewable energy. Certainly in our children's lifetime, it has to be true. These renewables have a huge upside, Professor Engelder said. In my view, subsidies for them are really very appropriate. There's no doubt about it, he said, adding that the payout might not happen until 2042. And here's where Terry and I differ. 2042 is too late. That bridge, it's a bridge too far. We won't ever get to the other end, partly for the reasons he alluded to, which is every time we drill a new shale gas well, company has to go borrow about $5 million from investment bankers, taking your mutual funds in your retirement plans and loaning them to Chesapeake to drill that $5 million well. If we can convince that investment banker to invest that $5 million in renewables starting yesterday, then we can move renewables faster. But let me give you a little bit more detail on why it's too late. I've been showing this slide recently. It's probably the most important slide that I never did. I don't take any credit for it. It's done by a number of scientists around the world, all working on the 2013 version of the International Panel on Climate Control report. Everybody's waiting for it. So this is a prelude to what they're going to say. This squiggly line is a record of the change in average Earth temperature each year since 1900. The vertical axis is that temperature change in degrees centigrade. Here we were in 2010 when the last time was that they did this very detailed set of computer simulations that made these predictions. So this is actual measured data. No one disputes that except climate change deniers. These are computer projections, and here's the error, the possible error associated with each one of those colors. This purple line is business as usual. Keep developing and producing all the fossil fuels around the world that we're doing now, oil, coal, and natural gas. Burn as much as you can, as fast as you need it to keep the lights on and keep the homes heated. What those computer models say is that by the year 2042, the Earth's temperature will have risen by about 1.8 degrees centigrade. At that point, there will be no Greenland ice cap, no polar ice cap. Most of the Antarctic ice cap will be gone. The oceans will have raised about 4 meters. I didn't say 4 inches. I didn't say 4 feet. I said about 4 meters. Anybody own a home in southern Florida? You want to see what Manhattan looks like with a 5-meter high wall around it? Okay. That's where business as usual gets us. I won't go into the details right now. You can read about them. Don't have time. But the single most important thing that we could do to spend $1 tonight to allay climate change is to decrease the amount of methane being emitted into the atmosphere. It's too late for carbon dioxide. The carbon dioxide which is causing that was put into the atmosphere in the 1750s, the 1850s, and the 1950s. It's going to be there for millennia. But the methane that's causing that was put there in the last 10 years. So we can have a very abrupt effect on climate change by reducing methane. So what? Methane is very potent, much more potent than carbon dioxide. Up to 100 times more potent over the next 20 years, and that graph just showed you we only have about 20 years. We can't, as Professor Engelder just suggested, trade off economic development now for cooler temperatures at the end of this century. We don't have the end of the century. We have the remainder of our lives. Most of the people in here are only about 39. All right, so in 2011, Professor Howarth, Renee Santoro, and I published the very first paper. I'm bragging now for a minute. There had never been a paper published in the reviewed literature on what the effects were of shale gas emissions, methane emitted during the process of drilling, fracking, compressing, dehumidifying, processing, storing, transmitting, distributing, and burning. That's the life cycle of shale gas. No one had ever done an evaluation of how much methane doesn't get burned. And if it doesn't get burned, it goes into the atmosphere like those bubbles in that leaking well, and it does bad things. So we said in that paper, no one has really ever made really good measurements. There were hardly any measurements anywhere. The government hadn't done them, the industry hadn't done them, academia hadn't done them. 2 years ago, we said, start measuring. And there are now dozens of groups around the world doing those measurements. And the data is just now coming in. So what we predicted back in 2011 was what the data was done, the life cycle. That means everything that came upstream at the well site, everything that was midstream between the well site and the transmission pipelines, and everything downstream from the transmission lines to the time you burn it in your stove in your kitchen. We predicted that the emission rate was going to be somewhere between 3.6 and 7.9% of total annual production. That was a prediction. It wasn't a number, it was a range, because the data we had was really bad. So you don't make a number prediction based on bad data. You say, well, it could be this bad or it could be this bad. 2 papers have appeared. 2. In the last 6 months, where actual measurements were made. One in Colorado, here, in a non-shale gas basin. Remember, this is not shale gas yet. It's unconventional gas, but not shale. And this is only upstream and midstream. And the answer was somewhere between 2.3 and 7% of all the gas being produced in that basin in Colorado is leaking. It's not getting burned. More recently, in the Uinta Basin in Utah, up to 9%. These are refereed, journal, peer-reviewed publications. The data is being collected by NOAA, our federal government. So, we predicted between 3.6, 7.9 for all. These are only upstream, midstream. Unfortunately, I think we were conservative, and that's unfortunate. So the point here is, when the dust clears and the science is done and all the measurements have been made, I will stand here and state my claim on my reputation and my wife's good name that somewhere around 5 or 6% of all the natural gas being produced in the United States today never gets burned, it gets vented. And that's really, really bad for climate change. All right, another paper that just appeared last week. How old are the gas lines, the gas mains under the city of Boston? Some of them over 100 years old, cast iron with hemp joint filler. So a colleague of ours at Boston University just published a paper last week. He drove 790 miles of streets in downtown Boston using a very high-tech instrument to measure what the methane concentration is along the streets. And what he found was this. Every one of those numbers is parts per million. So you'll see every one of these yellow lines is above the background level, the natural background level of methane in this room. You're breathing about 2 parts per million methane. That's natural budget on the earth. Anything above that is bad. And what he's seeing is that there's a hell of a lot of leakage going on in downtown Boston. Another reason why we think that our estimates are wrong. And now you might say, why don't they just fix this? Why don't they fix the leaking wells? Why don't they fix what's happening in Colorado and Utah? Why don't they dig up all the streets of Boston and replace all the pipes? That's capital investment. Once again, we're back to that moral uncertitude. I don't think there's any moral uncertitude. Should I spend $1 of my tax dollars, federal tax dollars, helping the city of Boston repair its leaky pipelines? Hell no. I'll spend it on windmills and solar panels. So here's the answer. An answer. Politics always begin at home, and this is basically a political question. As Professor Engelder said, we have to make a trade-off. So I've been working for the last 3 years with a number of other people, a large number of people around the world, with an alternative to shale gas for New York. I've been accused by EID and ANGA of being Mr. No. Well, Professor Ingraffea, if not shale gas, then what? This. So, it is absolutely technically feasible that by the year 2030, New York State will be effectively completely off fossil fuels. I didn't say the world, I didn't say the United States. You do what you can do here. First, you do it in your home, then you do it in your community, then you do it in your town, then you do it in your state. Pick the low-hanging fruit where you can have effect. Professor Engelder rightly pointed out the U.S. has to be the leader in this. New York State can be the first. So here's what it looks like, and it's not just wind and not just solar. Professor Engelder is right. The sun doesn't shine all day long. The wind doesn't blow all day long. So you have to have a portfolio. And the portfolio looks like this. About 10% onshore wind. That's 4,000 turbines. 40% offshore wind. It's 12,000 turbines. 10% concentrated solar. 10% solar PV plants. 6% residential rooftop. Anybody have PV on the roof yet? Okay. 12% commercial government rooftops, 5% geothermal, 0.5% wave, 1% tidal, and 5.5% hydroelectric, which we almost already have in New York. Now you're sitting there saying, wait a minute, whoa, that's a heck of a lot of work. Compared to what? 50 to 100,000 wells? That's a hell of a lot of work. 8 to 16,000 pads, that's a hell of a lot of work. A lot of cement, a lot of concrete, a lot of earth moving, a lot of CO2. 5 to 100 compressor stations, 500 to 1,000 compressor stations, this is New York. Thousands of miles of new pipelines, thousands of incidents of well water contamination, increased New York's contribution to global warming, and this is the kicker. You know all that steel that they're now advertising, saying, in the commercials that ANGA runs on TV, up to 6 layers of steel and cement protecting your groundwater? That's 100 tons of steel per well. And once they put it down there, it doesn't come back. It's not recyclable. So if we put 100,000 wells in New York, we will put effectively 2.5 times the total tonnage of the United States Navy in steel underground. Gone forever. Anything you build on the surface, hold on, oops, all that stuff, that's recyclable. So all those things combined result in a balanced production of electricity. We will be an all-electricity state. Yes, the sun doesn't always shine. Yes, the wind doesn't always blow. But with storage and smart grid, and we don't have to worry about transformers burning out, and with all that mix, we can show, technically, that this can be done. Okay, what are the other effects? I got 1 more minute. Let me wrap it up. Reduce New York's end-use power demand by 37%. Not by conservation, but by the mere fact that electrical power is much more efficient than burning fossil fuels. It takes much less energy to drive your car a mile on an electric motor than it does to drive your car a mile on gasoline. 30% more efficient. So if you convert New York State effectively to all electricity, that is, gradually wean ourselves off of heating our homes, and generating electricity with natural gas, and generate it using all those other technologies, we immediately begin to decrease the actual energy demand from the state. Roughly 58,000 new jobs, permanent full-time jobs. Reduce New York air pollution mortality. We do kill people when we burn natural gas. Natural gas is a fossil fuel. It also helps create smog. Okay. 4,000 people per year in New York die from air emissions. Natural gas contributes to that. All right, finally, 2 good reasons for doing much more quickly what Professor Engelder and I completely agree have to be done eventually. We just differ on how quickly. He says take longer and use natural gas in the meantime. I say we don't have to start mining natural gas in New York. We can start producing homegrown, energy independent, energy secure, fixed cost. What's the cost of the sun? What's the cost of the wind? There's no fuel cost. So you can be absolutely sure that wind, water, and solar energy will provide a stable, renewable source of electric power, not subject to the same fuel supply limitations as fossil fuels, because fossil fuels are not renewable. The demand keeps going up, the supply keeps going down, therefore the price keeps going up. Not true with renewables. And there's a lot of stuff being said in the literature right now and in the newspapers about how we're now going to use our oversupply of natural gas as a foreign policy cudgel, and to prove that we can increase our balance of trade. That's all being made up by the industry as they went along. They don't know what to do with the gas. Thank you. We own the wind, we own the sun, we own the water. They make us truly energy independent and energy secure. So thank you very much.